All right, thank you for the introduction. So, Mitch Burnett, I'm a research engineer at BYU Radio Astronomy Systems Group, and I'll be talking to you about the ALPACA Beamformer, our digital backend development, where we're at, where we're headed, and what we're up to. So ALPACA is the advanced L-band phased array camera for Arecibo. Recently awarded, it's a 4-year project. We're just approaching our 1-year mark. Collaboration between us at BYU, Cornell, and the University of Central Florida. Cornell will be providing and developing the PAF front-end, electronics, array elements, Dewar cryogenics. At BYU, we're responsible for the overall project management, development, moving it forward, as well as the signal transport, downlink, digital beamformer backend, user interface, and interfacing with Arecibo. And then come installation, we'll receive a lot of help from the University of Central Florida to do that. And astronomical paths, they're finding their way onto a lot of our telescopes throughout the world. At BYU, we've had experience with L-band 20-meter path within our NRAO and a millimeter wave. And then most recently, about 2 years ago, we finished the focal L-band array, FLAG, on the GBT. It's a 19-element dual polarized elements with a digital backend capable of processing 150 megahertz of instantaneous bandwidth and simultaneously forming 7 beams on the sky. It's a pulsar transient detection instrument along with neutral hydrogen. And we're taking a lot of that architecture, expanding it, and moving it over into ALPACA. And so we've seen through the week here the narrowband beamformer digital design, where we can take our array of sensors and apply a steering vector to steer and form beams in the direction that we need. And for paths in radio astronomy, this provides several capabilities by being able to densely pack simultaneous beams, increasing the field of view, and even the potential of adaptive RFI cancellation. And so that really drives what paths are all about, to increase the field of view, increasing the survey speed, and sky mapping capability. And so comparing the current 7-beam receiver on alpha, we can see that ALPACA's simulated field of view will extend and increase a lot of its capabilities. And so, again, ALPACA, our kind of primary science targeted cases are for very fine spectral line observations and transient observations, and as a survey mapping instrument. And so our architecture, what this looks like is we'll have the cryostat cooled LNAs up in the receiver dome with signal transport on RF over fiber boards, modules that we're developing, into the digital beamformer backend, with we have the F engine, X engine, and beamformer. So I'll throw up kind of our high-level specs where we're at right now. I'll kind of talk through a few of them. You can digest some of the others. But we are an L-band with the analog front end of 420 megahertz. The digital backend will process a little more than 300, forming 40 simultaneous beams. Our channel width and how we have it set up to do the coarse or the pulsar transient and fine mode is we take a 2-stage approach where the coarse is channelized in an oversampled PFB in the F engine, with the fine channels formed in the GPU in the back end. And so those coarse channels from the F engine will be around 320 kilohertz, but then the fine channels will be there will be 36,000 of them at 5 kilohertz. Our first stage PFB is 2048, 4/3 oversampled, and our second stage will do a 64-point polyphase filter bank, which will be the critical polyphase filter bank, critically sampled polyphase filter bank. To achieve all this, we'll be using 18 of the ZCU 111s with 25 HPCs on the back end, each containing 2 GPUs for a total of 50. And then we'll have reduced bandwidth modes, being able to swap in, swap out various bandwidth capabilities. And we're a very familiar architecture where we continuing to use the heterogeneous approach, as I mentioned, with on the front end, or just digitizing the F engine. We have our FPGAs, ZC111s, over 100 gigabit Ethernet network, where we then, through the corner turn, frequency distribute the data for all elements across the 50 GPUs. And we're really excited about our board. We've seen this several times this week now. And inside our F engine, we will be implementing the oversampled polyphase filter bank. And why are we doing that is so we, as I mentioned, so we can do this two-stage zoom approach where we can provide coarse channels appropriate for beamformer calibration and pulsar detection, but then in a second stage do finer channelization for transient line observations. But this two-stage approach, there are some issues. As with any spectrometer, if you don't design it correctly, you can get spectral leakage or scalloping loss, which is why we typically use the polyphase filter bank. And but if both channelizers, both polyphase filter banks are critically sampled, the first stage produces scalloping and aliasing in the second stage. And so I'll kind of walk through some simulations that kind of highlight that. Some of you are maybe familiar with it. So we've seen this, the polyphase filter bank. Here's a simulation for 2048 PFB, 8 tap branches, and termed the critically sampled. So in your first stage, this looks great. You wouldn't see the scallops in your spectrometer. However, when you take it through a second stage, it traces out the notches or the scalloping, and if a tone were to be inserted within this channel overlap region, it's aliased over. And here's a measured example of that. We have a tone right in our overlap, aliased in. Another tone, it's correctly in the right channel. We see it in its bin. But then also the undesirable artifact is that we have the scalloping loss, a non-uniform passband. And so what do we do about this? Well, so our approach is to use the oversampled polyphase filter bank, and that can be derived by extending the conventional critically sampled polyphase filter bank. And it's termed critically sampled because the outputs here on the end are new time series at rates of Fs over m. The PFB, as we've learned, uses properties of the sampling theorem to efficiently capture narrow band channels, equivalent to downsampling. But the duality of these properties indicates that we can do the same by upsampling. And so to achieve this, we modify the decimation rate, which therefore increases spectral overlap, and we can discard redundant channels, producing a flat spectrum. And so this modification comes about by picking a decimation rate, anything less than the the critically sampled rate m. And what the effect is that the outputs are now oversampled by a ratio of m over d, and the decimation is done by now modifying how we introduce new samples into the polyphase filter bank. So instead of starting at port M, we now start at port D and commute samples through the filter bank, shifting old samples through the filter by D and delivering D new samples. This isn't done for free because these shifts by D, a time shift introduces a frequency-dependent phase shift not accounted for in the kernel by the FFT, in the e to the j 2 pi over m. And so how this is done to compensate for this is by putting circular buffer between the output of the FIR stage and the input of your FFT. And this serves to realign the M-path filter outputs with their correct corresponding FFT input. And so how this circular buffer is formed is dependent upon that oversample ratio, m over d. And it's determined as the numerator of the improper fraction. And so to provide some sense to this is a digital TV demodulation. This is a common approach for even today in digital TV. An example is a 64.0 oversampled polyphase filter bank with a decimation rate of 48. So that oversample ratio is 4/3. The 4 indicates how many shift states that there are in accomplishing this. And so what this looks like is on state 0, all the samples just get clocked over. In state 1, you advance up by 16. State 2, everything's advanced by 32. And in state 4, everything's advanced by 48, finding their appropriate spots. And what we get is we get that increased spectral overlap in the channels, and we can throw away some of the discard the redundant channels, and now we've removed in the second stage that the scalloping loss and the effects of aliasing. And so to provide some sort of intuition when designing polyphase filter bank in general, and now the oversampled polyphase filter bank, when you pick D, as D, the decimation rate decreases from the critical rate, or the transform size M, this increases the aggregate data rate out of your FPGA. And then as P, the filter taps per polyphase branch increases, the response of each narrowband channel has sharper transition bands and lower side lobes, but increases your overall total usage. I think we all kind of know that, and it's a pain. We want the best filter, but our FPGA is only so limited. But for ALPACA, what we're going to really need to be careful about is we need 8 inputs per FPGA, and so 8 of these parallel implementations will be pretty expensive, and that's what I've been working on mostly in the beginning months of the project, is to understand the filter bank, implement it, and right now it's in a standalone implementation that I've done in HLS. And I was talking to Patrick yesterday. Sounds like I'm the poster child for Xilinx here. I did this in HLS, prototyped it quickly, have it in my pink Jupyter notebook, and it's working really great for a quick prototype to really kind of understand what we're kind of expecting on our FPGA. And everything's available. You can grab my HLS code, the Vivado project, which will generate this project and step you through a Jupyter notebook. But it's just, I have an oversampled polyphase filter bank, a DMA engine, and my MP sock. I'm generating samples in Python, shifting them out DMA over to the oversampled polyphase filter bank, bringing them back, and then doing the second stage, FFT, in Python to show that there's no scalloping losses. And the utilization report out from Vivado, I compared it with another HLS implementation of the critically sampled polyphase filter bank. My version is parameterizable. I can change it from an oversampled rate to a critically sampled rate just by changing some preprocessor macros. And here's kind of what HLS is telling me right now. So for one of these implementations, these are its baseline resource usages. And I projected out, at worst case, linearly scaling up to my 8 parallel inputs. This is kind of where we're looking at for resources used. And this is only with some modest optimizations. I haven't really used HLS's full optimization capabilities that allow you to do even finer tuning resource management or how memories are accessed. And so I'm feeling pretty good about this. The next step is really trying to understand how the RFDCs take up in resource usage along with my Ethernet FIFOs. I imagine a lot of the rest of this will be taken up by Ethernet. Our back end, it's going to be these Tyan 2U GPU servers, each with 96 gigabytes. We're targeting the RTX 2080 Ti's GPUs. Feel like it looks like it'll be quite adequate for our needs. And our modes that we'll be offering, we'll be delivering kind of 2 modes, and then we have spec'd out several optional modes that we don't necessarily have funding for, but in doing a lot of the preparation and designing, we're trying to listen to SETI and other folks to have other backends. So we plan to multicast, but right now we're delivering 3 modes. And so in the H1 mode, we'll have a channel selection, bring in form our 40 beams, find PFB, old slide, it's now 64, do integration, and then output from a FITS formatter to a Lustre array at Arecibo. In the transient mode, we're just effectively removing the polyphase filter bank, forming our 40 beams, doing the coarse fast dump integration. Our target is to do 64 microsecond dumps. And then obviously a beamformer calibration mode to be able to calibrate your array steering vectors. And then one of the other modes I don't have here is an optional beam voltage mode where we would just stream beam voltages out to other multicasted backends. And we hadn't really had anybody talk about Hashpipe. We're targeting Hashpipe, and so I last minute decided to throw in some Hashpipe slides to put that one out there as we talk about other backends. If I say anything wrong, I'm going to leave it up to Dave to correct me. But I'm a user now for several years for Hashpipe, great. But it's a generalized framework for processing. It does a lot of the heavy lifting you don't have to worry about and required to implement a multi-thread application. There's some IRQ and core affinities. You have to go and figure that out, but you tell that to Hashpipe, it'll take care of all of that for you. And a plugin is a group of these tasks, and so they're separated by ring buffers controlled by semaphore arrays, and so a group of these threads joined together creates that plugin. And it's really generally flexible, and it's up to the developer to implement how these tasks operate with several functions, just controlling the access patterns of this ring buffer. And so for ALPACA, our generic ALPACA Hashpipe plugin will kind of look like this. There will be three main tasks: intercept packets off the network, throw them into the ring buffer, start our GPU accelerator thread, crunch out the calculations, drop them in another array, and then out to the FITS writer. And each of these tasks are monitored and communicate through a shared key value buffer, and then coordination among all of our nodes is through our MNC backend. And so right now, where we've been, where we're going, just kind of really high level. The project started in August. I joined the team around November, so I missed the kickoff meeting. December, January, we got our board, and then been really playing with the ZC111 since February. July, we had our preliminary design review. Now we're in first stage designs. We have our RF over fiber board back. We're testing that out. We're narrowing in on antenna element design. The cryogenics are being designed. So then in this next year, in July, we'll have our critical design review, and then hopefully a full-scale integration test at BYU September 2021 with delivery in March of 2022 and commissioning in June of 2022. And I just wanted to add kind of one slide depicting where we're kind of at on Casperizing the ZC111. I attended the Casper hardware porting shop in South Africa with the goal to port the board, or at least learn how to. It was, of course, it's a monstrous task to do, and I'm relatively new to that. We've been users of Casper at BYU for years, but now trying to become a developer for it. And we managed to get this similar analog to tutorial 1 for the red PTI to work. So we have a yellow block for the ZC111 that configures system generator correctly, and exposing our AXI to talk to registers, counters, the have you. And so next steps kind of from here out are, there's a working group here trying to figure out what we're doing. We're talking primarily about ADCs, what that will look like. I've tried to understand the ADC as much as I can to try and get the expert Casper users to tell me, okay, Mitch, here's how you take it, make it a yellow block. If there's anybody else interested with very good ADC, RFDC configuration, come find us in the working group. That way you can have input and kind of insight to help us know what we can do to give the best availability of the yellow block in Casper. And so there you go. Jason was first.
The HLS compiler you did with your oversampled PFP,
yeah.
What sort of speeds could you run at that? I mean, I noticed
yeah, so this is running at, I'm clocking at 300 megahertz.
Okay, and you achieve timing there pretty easily?
Yeah, no problem. I didn't even have to touch it once. I guess, Jeb?
Yes, I mean, I don't have time for more,
okay.
but I can
We'll talk later, Jim.
afterwards. Yeah, let's thank Mitchell one more time.